Hello friends, welcome to my lecture on Morera's theorem, Liouville's theorem, fundamental theorem of algebra. We are going to discuss the consequences of Cauchy integral formula and Cauchy integral higher order Cauchy integral formula. So, suppose we first discuss the Morera's theorem. If fz is continuous in a simply connected domain D, if integral over C fz dz equal to 0 for every closed path in D, then fz is analytic in D. So, let us prove this Morera's theorem. It is the converse of the Cauchy integral theorem. So, we are assuming that fz is continuous in a simply connected domain D and integral over C fz dz equal to 0. So, let us say this is your domain D, okay, and C is any simple closed curve in D, okay. We are given that integral over C fz dz equal to 0. So, by the continuity of fz, integral over C fz dz equal to 0 implies that the integral over C fz dz is independent of the path we can write integral over A to B fz dz is independent of the path joining A and B inside D. So, you take any 2 points A and B in the domain D, you join them by any path, okay. The integral over A to B fz dz will always be same. This follows by the continuity of fz and integral over C fz dz equal to 0 by, because if you take any point here, okay, then integral over C, let us say this point is A, this point is B, okay. So, integral over C fz dz we can write as, let me call it as A point, this is say B, this is some E point, this is F, okay. So, integral over A E B F, A E B F A fz dz equal to 0, okay. We can write it as integral over A E B fz dz plus integral over B f A fz dz equal to 0, or we can say this follows because when we assume fz to be continuous, integral over C can be written as integral over C1 plus integral over C2, where C1 and C2 are the two parts of the curve C. So, integral over AEB plus integral over BFA, and this is equal to integral over AEB fz dz equal to integral over when we take this term to the other side, it will become minus integral over B of A fz dz. So, it will be A of B. Okay. So, integral from A to B in the anti-clockwise direction A E B is same as integral from A to B by the curve through the curve A of B. Okay. So, integral of fz from A to B does not depend on the path which joins the point A to the point B, it depends only on the endpoints. So, by the continuity of fz, when integral over C fz dz equal to 0, integral over A to B fz dz does not depend on the path which join the point A to B, it only depends on the endpoints A and B provided they lie inside D. Okay. Now, let us consider the function fz equal to integral over z naught to z f w d w. Okay. We can write it as from this we can, if z plus delta z is a point, z is any fixed point, let me say z is a point here in w in D, okay, and z plus delta z is another point in D. Okay. So, f z plus delta z will be equal to z naught to z plus delta z f w d w, and then what we will have, f z plus delta z minus f z equal to integral over z naught to z plus delta z f w d w minus integral over z naught to z f w d w. Okay. So, f z plus delta z minus f z will be equal to integral over z naught to z plus delta z f w d w minus integral over z naught to z f w d w, and this will be equal to integral over z to z plus delta z of f w d w. Okay. Now, what we will do, let us divide f z plus delta z minus f z by delta z, okay, and subtract f z. Then what will happen? This will be equal to integral over z naught to z plus delta z f w minus f z d w 1 over delta z, because z is fixed. So, f z is a constant. So, integral over z to z plus delta z f z d w will be equal to f z will come outside, and we will have z to z plus delta z d w equal to delta z, which will cancel with this delta z, and we will get f z. So, this can be written like this. Okay. Now, by the continuity of f z, okay, by the continuity of f z, it follows that z is a point inside D. So, by the continuity of f z, it follows that for a given epsilon greater than 0, there exists a delta greater than 0 such that mod of f w minus f z is less than epsilon whenever mod of w minus z is less than delta. Now, let us draw the figure again. Suppose this is our domain D, okay. Here is the point z, z plus delta z is another point in the neighborhood of z. Okay. We are given that mod of f w minus f z is less than epsilon whenever mod of z minus w minus z is less than delta. Now, we have already seen that integral over a to b f z d z is independent of the path joining a to b. So, this integral, okay, integral from z to z plus delta z is independent of the path which joins z to z plus delta z. So, since integral over z to z plus delta z f w minus f z d z d w is independent of the path joining z to z plus delta z. So, we can consider the line segment joining z to z plus delta z. Okay. So, let us consider this line segment which joins z to z plus delta z. Okay. Then, if we take delta z to be sufficiently small, that is mod of delta z less than delta, okay, mod of delta z less than delta, then what will happen? Integral over then mod of f w minus f z for all w belonging to the line segment z to z plus delta z will be having the absolute value less than, then mod of 1 over mod of integral z to z plus delta z, okay, f w minus f z d w. Okay. We can take delta z also here. This will be less than 1 over mod of delta z, this 1 over delta z, and then mod of f w minus f z will be less than epsilon, because this is valid for all w which satisfy mod of w minus z is less than delta. So, if you consider w point w which lies on the line segment joining z to z plus delta z, and you are taking mod of delta z less than w less than delta, then this will be less than epsilon into mod of delta, and we will get epsilon. Okay. So, this will imply that mod of this is less than epsilon when delta z is sufficiently small, which implies that limit delta z tends to 0, f z plus delta z minus f z divided by delta z is equal to f z. So, by the definition of the derivative, this is left hand side is f prime z. So, f prime z is equal to f z. So, this means that f prime z exists at any z belonging to D. And which means that f prime f z is an analytic function in D. Now, we have already seen that if f z is an analytic function, then all ordered derivatives of f z are also analytic. So, this implies that f prime z is an analytic function in D. Now, f prime z equal to f z, okay, but f prime z is equal to f z. So, f z is analytic in D. So, this is the proof of the Morera's theorem. Okay, now, let us go to Cauchy's inequality. So, this is a consequence of higher order Cauchy integral formula. Let f z be analytic in a domain D. Okay. Let f z be analytic in a domain D and C be a circle of radius r C be a circle of radius r with center at z naught. Okay. In D, then mod of f n z naught is less than or equal to n factorial into m over r to the power n, where m is the maximum value of mod of f z over the circle mod of z minus z naught equal to r. The equation of the circle, this one, let me call it as C. So, then C is mod of z minus z naught equal to r, because its center is at z naught and radius is r. Okay. Now, we know that the f n z naught is equal to, by Cauchy integral formula, higher order Cauchy integral formula, n factorial by 2 pi I integral over C f z d z divided by z minus z naught to the power n plus 1. Okay. So, mod of f n z naught will be equal to mod of n factorial by 2 pi I integral over C f z dz divided by z minus z naught to the power n plus 1. Okay. Now, mod of iota is equal to 1. So, this is n fact mod of this is equal to mod of n factorial divided by 2 pi and then mod of integral over C f z dz divided by z minus z naught to the power n plus 1. Okay. Now, mod of f z is less than or equal to m. Okay. For all z lying on the circle C. Okay. So, mod of f z divided by z minus z naught to the power n plus 1 is less than or equal to m over mod of z minus z naught to the power n plus 1 means r to the power n plus 1 for all z on C. Okay. The length of C is 2 pi r. It is a circle of radius r. So, mod of integral over C f z dz divided by z minus z naught to the power n plus 1 is less than or equal to m by r to the power n plus 1 into 2 pi r. Okay. R we can say 2 pi m divided by r to the power n. 2 pi m over r to the power n, and hence a mod of f n z naught is less than or equal to n factorial by 2 pi into 2 pi m by r to the power n, and we get the result n factorial into m by r to the power n. So, this is the proof of the Cauchy's inequality. We shall prove Liouville's theorem using this Cauchy's inequality. So, let us prove the Liouville's theorem. If f z is analytic and bounded in absolute value for all z in the finite complex plane, then f z must be a constant. It is a very important theorem. If function which is analytic in the whole finite z plane is an entire function. So, this theorem tells us that a bounded entire function is always a constant. Okay. Now, let us prove this. So, we are given that f z is bounded in absolute value So, there exists a constant m greater than 0 such that mod of f z is less than or equal to m for all z in D. Okay. Now, let us take the circle with center at z naught. So, mod of z minus z naught equal to r. Okay. This is r, this is z naught. Okay. Then, by higher order Cauchy integral formula, we have f prime z naught, or by the Cauchy's inequality, mod of f prime z naught is less than or equal to n factorial into m by r to the power n. So, less than or equal to n is equal to 1. Okay. So, 1 factorial is 1, and so m by r. Okay. So, mod of f prime z naught is less than or equal to m by r. Z naught is an arbitrary point in the domain, in the whole complex plane. You can take any point z naught and draw a circle with z naught as center and of radius r. So, then mod of f prime z naught is less than or equal to r. Now, since r can be taken as large as we please. Okay. So, since r is completely arbitrary, we can take it as large as B, please. So, taking letting R go to infinity, we have f prime z naught equal to 0, okay, where z naught is arbitrary. Which means that f prime z is equal to 0 for any z, for any finite z. Okay, which implies that f z is a constant. So, in order to prove that f z is a constant, let us say let f z be equal to u x y plus I b x y, then we know that f prime z is equal to u x plus I b x. Okay. Since f prime z is equal to 0, we have u x equal to 0 or b x equal to 0, but by CR equations u x equal to b y and u y equal to minus b x. Okay. So, u x equal to 0, b x equal to 0 gives u y and b y are also zeros, which means that u and v are functions of x y such that their partial derivatives with respect to x and y are zeros, and therefore, u and b are independent of x and y. So, u is a constant and v is a constant, and hence f z equal to u plus I v is a constant. Let us now prove the fundamental theorem of algebra. If f z is a polynomial in z, not a constant, okay, then f z is equal to 0 for at least one value of z. F z will have at least one root that which will make it 0. Okay. So, f z is equal to 0 for at least one value of z. So, let us say f z is equal to sigma I equal to 0 to n a I z to the power I, that is we are writing f z as a naught plus a 1 z plus a 2 z square and so on a n z to the power n. Okay. So, let f z be sigma I equal to 0 to n a I z to the power I, which is same as a naught plus a 1 z plus a 2 z square and so on a n z to the power n, and we are taking n to be greater than or equal to 1. We do not allow n to be equal to 0, because if n is allowed as 0, then f z will become a constant. So, n is greater than or equal to 1, and moreover that a n is not equal to 0, so that it is a polynomial of degree n. Okay. Now, suppose f z is not equal to 0. So, we are going to prove this fundamental theorem of algebra by contradiction method. So, let us assume that it does not vanish for any value of z. Then we can consider the reciprocal of f z, that is 1 over f z as g z function. Okay. So, let us consider g z equal to 1 over f z. Since f z is analytic in the f z is a polynomial, so it is analytic for all z, and 1 over f z is not 0 for any z. So, g z is analytic for all z. Okay. Now, f z is analytic for all z, g z is analytic for all z, and also mod of g z equal to 1 over mod of f z, which is equal to 1 over mod of a naught plus a 1 z and so on a n z to the power n. We can write it as mod of z to the power n and then mod of a n minus mod of, because mod of z 1 minus z 2 is greater than or equal to mod of z 1 minus mod of z 2, or we can say 1 over mod of z 1 minus z 2 is less than or equal to 1 over mod of z 1 minus mod of z 2. So, we are making use of this triangle inequality 1 over mod of a naught plus a 1 z and so on a n minus 1 z to the power n minus 1. This we are considering as one complex number, and the other is a n z to the power n. So, then I can write it as less than or equal to 1 over mod of a n into mod of z to the power n, okay, minus mod of a naught plus a 1 z plus a 2 z square and so on a n minus 1 z to the power n minus 1. Okay. And when I write it, we can also write it like this, 1 over mod of z to the power n mod of a n minus mod of z to the power n we divide here. So, it will become a naught by z to the power n, a 1 by z to the power n minus 1 and so on a n minus 1 upon z. Okay. So, this is what we get, a n minus 1 upon z, a n minus 2 upon z square, a 1 upon z minus 1, a naught upon z to the power n. Okay. So, this is mod of g z is less than or equal to this. Now, let us choose a real number m to be greater than 1, okay, and such that m is greater than mod of 2 n a j over a n, okay, for j equal to 0, 1, 2 and so on up to n minus 1. Okay. So, when we do this, what we have is the following. Then for mod of z greater than m, we have mod of a j over z to the power n minus j less than or equal to mod of a n over 2 to the power n. How we get that? Let us look at this. M is greater than mod of 2 n a j divided by a n, where j takes values 0, 1 and so on up to n minus 1. Okay. So, this I can say mod of a j is less than m times mod of a n by 2 n, okay, for j equal to 0, 1 and so on up to n minus 1. Okay. Now, if I consider this mod of a j over z to the power n minus j. Okay. So, then this will be less than or equal to m mod of a n over 2 n, and mod of z is greater than m, okay, m is greater than 1. So, mod of z greater than m implies that mod of z to the power n minus j, okay, is greater than m to the power n minus j. Okay. So, this is m to the power n minus j. Okay. And m over m to r, you can say mod of a n upon 2 n m to the power n minus j plus 1. Okay. So, this is always less than or equal to mod of a n divided by 2 into n, where j takes values 0, 1 and so on up to n minus 1. Even when j equal to n minus 1, n minus 1 plus 1 will be equal to n, and we will have m to the power 0. So, we will have 1. So, mod of a j over n to z to the power n minus j is less than or equal to mod of a n over 2 n for all j from 0 to n minus 1. Okay. Now, mod of g z, okay, this is mod of g z. Mod of g z is less than or equal to 1 over mod of z to the power n, and then we have mod of a n minus mod of a n minus 1 over z, a n minus 2 over z square and so on, a 1 over z to the power n minus 1 plus a naught over z to the power n. Okay. So, mod of these are n terms, okay, these are n terms. So, mod of each term here is less than or equal to mod of a n by 2 n. Okay. So, mod of a n minus 1 by z plus mod of a n minus 2 by z and so on mod of a naught by z to the power n is less than or equal to mod of a n minus 1 by z plus mod of a n minus 2 by z square z square and so on mod of a naught by z to the power n. Okay. This is less than or equal to, these are n terms, each term is less than or equal to mod of a n by 2 n. So, mod of a n by 2 n into n. Okay. So, this will cancel and we get mod of a n by 2. Okay. So, what do we get? We have mod of g z, thus mod of g z is less than or equal to 1 upon, because mod of z to the power n is here. So, m to the power n and mod of a n minus mod of a n by 2. Okay. So, this will become 2 times m to the power n into mod of a n. Okay. Now, this means that now n is a fixed number which, because it is the degree of the polynomial. So, mod of g z is less than or equal to 2 by m to the power n mod of a n for all z such that mod z is greater than m. Okay. Now, so thus mod of g z is less than or equal to 2 by m to the power n mod of a n, okay, for all z such that mod of z is greater than m. Now, what happens for mod of z less than or equal to m? So, when mod of z is less than or equal to m, okay, since f z is analytic, since g z is analytic, it is so it is continuous, and therefore, it is bounded, which means that there exists a constant k greater than 0 such that mod of g z is less than or equal to k for all z such that mod of z is less than or equal to m. Okay. So, when mod of z is less than or equal to m, mod of g z is less than or equal to k, and when mod of z is greater than m, mod of g z is less than or equal to 2 over m to the power n mod of a n. Okay. So, thus for all values of z, thus for all z belonging to C, okay, g z is bounded, is a bounded function, bounded in absolute value. And therefore, by Liouville's theorem, g z is a constant function for all z belonging to C. Now, let us recall that g z is equal to 1 over f z. Okay. So, this implies that f z is a constant function. Which is a contradiction to our hypothesis. Okay. We assumed that f z is not a constant function. So, this proves the fundamental theorem of algebra. Okay. So, this proves the fundamental theorem of algebra. Now, let us prove the Gauss mean value theorem. Let f z be analytic in a simply connected domain D. This is our domain D. C is a circle with center at z equal to a inside D. So, this is our circle C. The circle C is given by mod of Z minus A equal to say R, okay. Its radius is R. Then this theorem says that the mean value of Fz on the circle C, okay. Mean value of Fz on the circle C is the value of F at the center, that is A. Fa is mean value of Fz on the circle C. So, let us prove this. We have by Cauchy integral formula, Fa equal to integral over C Fz over Z minus A dz. Now, C is mod of Z minus A equal to R, and we are moving around C in the anticlockwise direction. So, we can write Z minus parametric form of C R e to the power I theta, where 0 is less than or equal to theta less than or equal to 2 pi. So, Z will be equal to A plus R e to the power I theta, 0 less than or equal to theta less than or equal to 2 pi. So, this will be equal to 1 over 2 pi I integral over 0 to 2 pi F A plus R e to the power I theta divided by Z minus A is R e to the power I theta, and dz is equal to dA is 0 because A is constant. So, R e to the power I theta into I d theta we have. So, I d theta into R e to the power I theta. So, this cancels with this, and we get I also cancel with I here, and we get 1 over 2 pi integral over 0 to 2 pi F A plus R e I theta d theta. So, this is how we prove Gauss's mean value theorem. Now, let us consider this problem. 1 over 2 pi we have to evaluate this integral. 1 over 2 pi integral 0 to 2 pi sin square pi I by 6 plus 2 e to the power I theta d theta. Okay. So, let us compare it with the Gauss mean value theorem. In the Gauss mean value theorem, we have F A equal to 1 over 2 pi integral over 0 to 2 pi F A plus R e to the power I theta d theta, where mod of Z minus A is equal to R. Okay. So, here we are given sin square A plus R e to the power I theta. So, if you compare this integral with this integral, okay, we notice that A is equal to pi by 6, R is equal to 2, okay, and Fz function, okay, Fz function is sin square Z. Okay. So, that F A plus R e I theta is sin square A plus R e I theta. Okay. So, by the Gauss mean value theorem, sin square Z is analytic in the whole complex plane. So, you can take any domain D, okay, which encloses this circle mod of Z minus A equal to R, that is mod of Z minus pi by 6 equal to 2. Okay. So, take any domain Z equal to pi by 6 is here, okay, pi by 6 is here, and you are drawing a circle. So, this you are drawing a circle with radius 2. Okay. So, this is mod of Z minus pi by 6 equal to 2, okay, and take any domain which contains this circle. Okay. So, Fz is analytic in this simply connected domain D, and it contains the simple closed curve, the circle mod of Z minus pi by 6 equal to 2. So, by Gauss mean value theorem, we have 1 over 2 pi integral 0 to 2 pi sin square pi by 6 plus 2 e to the power I theta d theta equal to f a, that is sin square pi by 6, and sin pi by 6 is 1 by 2. So, we have 1 by 2 square and we get 1 by 4. So, this is how we evaluate the value of this integral by using Gauss mean value theorem. Now, let us consider the function f z equal to u x y plus I b x y and take a to be x naught plus I y naught in the Gauss mean value theorem. Okay. In the Gauss mean value theorem, Gauss mean value theorem gives f a equal to 1 over 2 pi integral over 0 to 2 pi f a plus r e to the power I theta d theta. Okay. So, a is any complex number and we are integrating here along the circle mod of z minus a equal to r. Okay. So, let us take a equal to x naught plus I y naught, then f x naught plus I y naught. Okay. F x naught plus I y naught is equal to 1 by 2 pi 0 to 2 pi. Okay. Here we have e to the power I theta is cos theta plus I sin theta. So, we get f of a plus r cos theta plus I r sin theta d theta. Okay. This means that f z is u x y plus I b x y, where z is r cos theta. So, f of z is r e to the power I theta, let us say. So, r cos theta plus I r sin theta, this is equal to u r cos theta r sin theta, and then we have I b r cos theta r sin theta. So, here also this will be 1 by 2 pi integral 0 to 2 pi u a plus r cos theta and then r sin theta. We are adding a to a means we are adding x, a is x naught plus I y naught. Okay. So, this will be x naught plus r cos theta, and here we will have I times y naught plus r sin theta. Okay. So, a is x naught plus I y naught. So, we will have x naught plus r cos theta plus I times y naught plus r sin theta. So, this will be u x naught plus r cos theta and then y naught plus r sin theta, and we have plus I b x naught plus r cos theta y naught plus r sin theta d theta. Okay. And left hand side is what? F x naught plus I y naught gives you u x naught y naught plus I b. Okay. So, equating real and imaginary parts, what we will get? U x naught y naught equal to 1 over 2 pi integral over 0 to 2 pi u x naught plus r cos theta y naught plus r sin theta, and b x naught y naught will be equal to 1 over 2 pi integral 0 to 2 pi b x naught plus r cos theta y naught plus r sin theta d theta. Okay. So, we get u x naught y naught equal to 1 over 2 pi integral 0 to 2 pi u x naught plus r cos theta y naught plus r sin theta d theta, and we know that u x by v x by are harmonic functions because they are real imaginary parts of the analytic function f z. So, mean value of the harmonic function u x by over the circle mod of z minus a equal to r is equal to the value of the function u x by at the center of the circle. Now, let us do one problem on this. Let us find the mean value of x square minus y square plus 2y over the circle mod of z minus 5 plus 2i equal to 3. So, here we are given the circle C as mod of z minus 5 minus 2i equal to 3. So, A is equal to 5 minus 2i and r is equal to 3. We have taken A equal to x naught plus I y naught. Okay. So, hence we have x naught equal to 5 and y naught equal to minus 2. Okay. It is easy to check that if you call u x y as x square minus y square plus 2y, then u x y is a harmonic function for all x y. It is harmonic function for all x y belonging to R cross R. Okay. Now, so in the complex z plane, you consider the circle 5 having center at 5 minus 2. So, 5 minus 2 means here. Okay. So, 5 minus 2 and draw the circle with radius 3. Okay. So, we will have some circle like this. Mod of z minus 5 minus 2i. Okay. So, by the mean value theorem for harmonic functions, u at x naught y naught is equal to 1 over 2 pi integral over 0 to 2 pi u x naught plus r cos theta y naught plus r sin theta d theta. So, the mean value of required mean value. Okay. Required mean value is equal to u x naught y naught. U x naught y naught means x naught square minus y naught square plus 2 y naught, and this means that 5 square minus minus 2 square plus 2 times minus 2. Okay. So, it comes out to be 17. One can directly verify, okay, by evaluating this integral. Okay. If you want to evaluate this integral, you need to write u x y in terms of x naught, y naught and r theta. Okay. So, if you want to do that, then u x y equal to x square minus y square plus 2 y. Okay. X is equal to x naught plus r cos theta. X naught is 5, r is equal to 2. So, we write 5 plus 2 cos theta for x, okay, square minus y naught is equal to minus 2. So, minus 2 plus r is equal to 3, this r is 3 here. So, here what we will have y naught plus r sin theta for y. Okay. So, y naught is equal to minus 2 plus 3 sin theta whole square, okay, plus 2 times y, that is 3 sin theta minus 2. Okay. So, what we will get 25 plus 30 cos theta plus 9 cos square theta, and then we get plus minus 9 sin square theta, and then we get plus 12 sin theta, and what we get is minus 4 plus 6 sin theta minus 4. Okay. This expression we integrate over the interval 0 to 2 pi and then divide by 2 pi. Okay. So, then this gets you, so this gives you then 1 over 2 pi integral over 0 to 2 pi. Okay. This is how much? 9 cos square theta minus 9 sin square theta. Okay. 9 cos square theta minus 9 sin square theta. Okay. 9 cos square theta minus 9 sin square theta. 12 sin theta plus 6 sin theta is 18 sin theta, and we have 30 cos theta. So, 30 cos theta plus 18 sin theta, and we have 25 minus 4 minus 4, so 17 plus d theta. Okay. So, the integral this they all integrals become 0 and we get 17 into 2 pi divided by 2 pi and we get 17. Okay. So, by putting the values of x and y in terms of x naught, y naught and r in the expression for u x y, and then integrating with respect to theta over the interval 0 to 2 pi and then dividing by 2 pi, we get the same value 17. So, this is how we can verify the mean value theorem in this case for harmonic function. With this I would like to end my lecture. Thank you very much for your attention.